Alright, silly people, here's the situation. We have a particle that's on a ring and it's moving around on the ring. Um, the ring has a circumference of L, right? And we are going to try and treat this like a quantum mechanical problem and get the wave functions, normalize the wave functions, and get the energy eigenvalues for the particle's motion. So, um, I'll say that the particle is a free particle technically. There's no potential in this problem, it's just moving around in a circle. So it has the Schrodinger equation for a free particle. Uh, this thing where k is defined as root 2me over h bar. But it also has this thing where, since it's moving around in a circle, if it moves a distance L, it is equivalent to not moving a distance L, I guess. So psi of x is equal to psi of x plus L. Um, and so that's kind of interesting. So the solution to this differential equation up here that I'm going to use is the a e to the ikx plus b e to the minus ikx form rather than the sine and cosine form. Um, and we're going to use the fact of the cyclical natures of the particle's motion and plug in 0 for that. So we're going to say psi of 0 equals psi of L, right? So that's going to be on the left-hand side, a plus b equals a e to the ikl plus b e to the minus ikl. And then we can solve this for a and be like it's a e to the ikl plus b e to the minus ikl minus b, right? Um, the other boundary condition, it's kind of a boundary condition, I guess, but we're going to plug in pi over 2k for x on both sides. This is going to be psi of pi over 2k plus L. This is going to be interesting because a e to the I pi over 2 gives you positive I, and b e to the I pi over 2, that gives you minus pi. And you get the same sort of thing over here. You get I pi over 2 e to the ikl plus b e to the minus I pi over 2 e to the minus ikl, right? So again, this is positive I, and this is negative I. Then we've got ia e to the ikl minus ib e to the minus ikl. The fact that it gives you i's isn't the interesting part. The interesting part is that now we have an a minus b instead of an a plus b. And we're going to come back to this equation after we do this next step. But right now, let's plug in what we have for a that we got from the first equation that we got. So we have a e to the ikl plus b e to the minus ikl minus 2b equals a e to the ikl minus b e to the minus ikl. And so the a terms get canceled out on either side. And now we have this equation, b e to the minus ikl equals b. This equation has lots of different solutions. And we're going to run through a couple of them. The first option we're going to look at is that this equation is solved trivially if b is equal to 0. That's pretty crazy. But if b equals 0, then we go back to this equation up here, where now we have a is equal to a e to the ikl. If you set a to 0 at this point, you just get that the wave function is 0, and we don't want that. Instead, the way to solve this is that a will not be 0. You can cancel them out, and we get 1 is equal to e to the ikl, and that means that kl is equal to 2 pi n, because any integer value of 2 pi represents a full cycle for the exponential. And then we can expand the expression for k in terms of e, and this is actually 2me over h bar, and then this is 2 pi n over L over here. And we can solve this for E for a 2 pi squared n squared h bar squared all over ml squared, right? We can even normalize the wave function as well, because now we know that psi equals a e to the ikx. So normalizing it is just integrating it from 0 to L, the mod squared of it, and so then that equal to 1. Since all that's in the wave function is a imaginary exponent, it's going to get canceled out when you take the mod squared, so we have a squared integral from 0 to L dx equals 1. That is a pretty easy little integral. It just gives you L, and so you find that a is 1 over root L, and then you can find that the wave function is just 1 over root L e to the ikx. And we're going to call this solution psi plus, since it's going to, with the positive e to the ikx thing, is going to represent clockwise motion, right? Or I guess it's counterclockwise, because yeah, positive direction is counterclockwise. But yeah, that's the counterclockwise solution. Option 2, going all the way back up to this equation up here, we can say that b is not equal to 0. This is option 2. And end up canceling out b on either side and just have e to the minus ikl equals 1. And that's going to give us the same quantization condition for KL, which means it's going to give us the same energy eigenvalues, and this is pretty interesting that they have the same eigenvalues. But if b is not equal to 0, then a has to be equal to 0 according to this equation up here that we got way back. So a equals 0, and we can write the wave function as psi equals b e to the minus ikx. We can normalize it again, same sort of process, equals 1, but now this is just b squared integral from 0 to L of dx, which again is just going to give you L. So you find that b is also equal to 1 over square root L. And you have that psi equals b, or it's psi equals 1 over root L e to the minus ikx. And we can call this psi minus because this is going to represent clockwise motion to this equation's counterclockwise. So what the hell? We have two wave functions that seem to have the same energy. And like a few videos ago, I think it was problem 244, we kind of proved that that can't be the case for one-dimensional problems. But the difference was, back then, is that we used the fact, this is kind of going back a little bit, but we use the fact that psi of infinity has to go to 0 for normalizable wave functions in one dimension. That's not the case for this one, right? Because it's just going around the circle infinitely. Psi of infinity for either of these looks more just like psi of x again, presuming infinity is divided by L, but yeah, you get the point. Um, it doesn't go to 0. So therefore, this case allows degeneracy. And I think you'll find, if you study any more problems like this, that if you have any sort of um, domain which is cyclic in one dimension, then you can have degenerate states in those as well. But in any domain that isn't cyclic, I think we can't have degenerate states in those. So, yeah, kind of interesting.